Okay, so it's time. We can start now, yeah? So, good evening. We are very happy to welcome today's speaker, Kyu-Hyun Chae. Kyu is a professor at Sejong University in Seoul, Korea. He obtained his PhD from the University of Pittsburgh in the US and did his postdoctoral research at the University of Manchester in the UK. Today, he will speak on observational evidence for the breakdown of standard gravity in favor of MOND-type modified gravity. So it's over to you, Q. Kindly speak uninterrupted for an hour, and then we'll have a Q&A session for 1 hour after your talk. Over to you. Thank you.
Thank you very much for the invitation. I'm very pleased and honored to speak at this network. So I'll describe the result in wide binaries. Okay, first of all, I think many of you are not so familiar with Korea. So let me introduce Korea briefly. We have some good ancestors and forefathers, and one of them is King Sejong, and he invented the Hangul, Korean alphabet system, and also supported science. And the Sejong University is named after King Sejong. Okay, I'll first give on rather important introduction. I think an important part of this talk will be the introduction, the current status and what are the points. And then I'll describe Gaia database and samples and the results, some results based on some specific methods, and I'll also compare with the other results, and then I'll conclude. Okay, so what are scientific measurements, inference, or knowledge? I mean, we need to ask this basic question, I think. Any measured value must be reproducible independently and repeatedly. If it is not reproducible, it is not a valid measurement. We know many false measurements in history of science that failed to be reproduced. And also, any required calibration must be done very carefully and accurately. I mean, this is the key thing. Some people tend to focus on some fancy algorithms or statistical methods, but what's more important is the basic. Also, I think transparency and understandability are also important. If a measurement involves complex steps, then every procedure must be transparent. A value just through a black box needs to be taken with caution. We need to be able to understand where the signal comes from. Also, robustness. Any claimed inference only through a specific method based on a specific sample is questionable. If a discovery has to be valid discovery, it has to be robust and reproducible. That's the key point. Okay, so gravity test with wide binaries, it essentially comes from measuring relative velocity or gravitational acceleration between two stars. So we already know that when the separation is less than 2 kiloastronomical unit, it must be Newtonian because we don't have any other theories or whatever clues to expect what otherwise, including MOND or whatsoever. So this is a very crucial thing. And also we use this to measure masses of stars. We know that when binaries are close enough, we know that they satisfy Newtonian dynamics. So we use Newton's third law to infer masses. Okay, now the question is here is when separation is greater than 2 kilo AU, the question is whether Newtonian dynamics holds or does it follow modified Newtonian dynamics? Yeah, that's the question here. Now I'll briefly describe MOND. So algebraic MOND says that it will deviate at a certain acceleration weaker than a certain acceleration. And so it will be Newtonian, much larger than this critical acceleration, but it will approach MOND behavior at a weaker acceleration. And we have this interpolating function between the two regimes. This is the basic tenet or principle or assumption of MOND. Now we have the specific MOND model called AQUAR. That is the classical and the oldest and still popular one to actually use to model data. And it is basically the modified Lagrangian theory. And so it gives modified Poisson equation. It's due to Milgrom and the late physicist Bekenstein. Okay, so what do MOND predict for wide binaries? Here, there is one important complication, that is the galactic external field. MOND is a nonlinear theory, so it requires external field effect. So when there is external field effect, it is very different from the algebraic MOND. So when the wide binaries are under the galactic external field that are actually larger than the critical acceleration. So external field effect is a big deal for wide binaries in for nearby galaxies. So when the external field effect is present, the prediction becomes like this red curve. So it will be a Newtonian down to 10 to the minus 8, and then it will switch, it will start to deviate from Newtonian, and then it will reach quasi-Newtonian. It's essentially another Newtonian, but with a rescaled gravitational constant. That's what the MOND gravity predicts under the external field effect. Now, for elliptical orbits, it's a little complex. Due to the eccentricity, it deviates regardless of this the modified gravity or whatsoever. It deviates just from eccentric orbit, but still we expect this deviation will be similar. Okay, that's the basic prediction. Now, the calculation with the computer, this is the prediction. Okay, so the black dashed curve is the algebraic MOND without external field effect. Now, with external field effect, it is very different. So it is almost Newtonian. And the difference is only just 40% or so. Okay. So this is what we can try to test with wide binaries. So in terms of separation, we expect it will be Newtonian up to 2000 astronomical unit. And then it will have a transition regime from 2000 AU to 5000 AU, and then it will become quasi-Newtonian. Now, what are the basic data? Here, the basic data are sky projected separation and sky projected velocity, not separation in real 3D space or real relativist velocity in 3D space. What we measure are these sky projected values. So the basic key quantity is tangential velocity on the plane of sky and this sky projected separation. And we can measure this sky projected velocity from the proper motions. Astronomers call proper motions the angular movement over time. We call them proper motions. Okay, so since these wide binaries are very far away from terrestrial standards, actually we can use the plane geometry. I'll get back to this perspective effect later, but when the separation between two stars is small compared to distance, which is the case here, we can just use plane geometry. So we can turn the proper motion to projected velocity. Now, what are methods to test infer gravity at low acceleration? Okay, the first method is velocity profile test, actually stacked velocity profile test. That is checking, testing how projected velocity scales with the separation. This was first introduced by Javier Hernandez in 2012. And also one can do more detailed analysis, namely distributions of this projected velocity in bins of separation. Okay, this is what I did just recently. So for this test, we require median total masses should not vary with S. If only this scaling should be used. If Newtonian predicted values are Monte Carlo generated for binaries, then distributions of theoretical distributions of this projected velocity and measured projected velocity can be compared in bins of S. So maybe one can somewhat relax the strict requirement on total masses. And we need a good precision for proper motions for this test, and also a reasonable or sufficient signal to noise for projected velocity itself. This method is the simplest and the most straightforward method, and it is well suited for pure binaries. Here, what I mean by pure binaries are binaries, they do not have hidden close companions. But it can also work when apparent binaries include hierarchical systems if the fraction of hierarchical systems does not vary with S. For a median total mass, it is easy to know where the MOND prediction starts to deviate. As I mentioned here. So in this test, we know where the MOND deviation should occur. So that's the good advantage. So this is an early attempt based on Hipparcos data more than 10 years ago. But here, signal to noise is 1.7, here 0.5. So this is just an attempt. So from measurement standard, it's not too meaningful, but it is important that this idea was introduced. Okay, this method is similar to where physics started more than 300 years ago. Kepler discovered this scaling solar system. And so in a sense, we are extending this. But in this case, all planets orbit according to one potential of the sun. But in binaries, actually, each system is individual system. So that's why I mentioned the median total mass should not vary with the separation. So the method is statistical, but the basic concept is similar to actually this rotation curve in solar system. So we try to extend this rotation curve to much larger separation with two stars orbiting each other. Also, it may be similar to rotation curve in galaxies. In this case, also, all particles follow the same potential. Okay. Now, the second method is ballast ratio or V tilde distribution test. Okay, so one define a ratio of projected velocity to circular velocity at the separation, at the projected separation, or the 3D velocity, the recovered 3D velocity by the projection over circular velocity at projected separation. So one obtains a distribution or a histogram for a certain range of S and try to test using this distribution, test gravity using this distribution. So for this method, both numerator and denominator have measurement uncertainties. So a careful data control is necessary. And also, we need to predict the distribution very carefully with the model, because unlike the previous method, it is not obvious where the distribution should differ from the Newtonian prediction. So it is a rather indirect method, although it seems popular by some people. So this gravity is actually indirectly related to this V tilde, and it is not so obvious where and how the MOND V tilde distribution starts to deviate from the Newtonian prediction. So this is the actually main problem I had with this method. So I introduced acceleration plane test that was published this summer. So what I do is basically I use Monte Carlo method to reconstruct the actual Newtonian gravity and the observed gravity. So this is the Newtonian centripetal acceleration that two stars experience. And we can define the kinematic acceleration with relative velocity. So we measure the projected velocity. So we have to projected velocity to actual velocity. So it's it's a reconstruction method with Monte Carlo technique. Okay, so for this method, we need general quality control on data, and we need the MOND predicted scaling relation to compare with the recovered relation. So this is just a direct way of testing gravity, because MOND relation is, as you see, just a relation between Newtonian gravity and measured gravity. So I try to directly test this relation. So we know exactly where the prediction should start to deviate from the Newtonian prediction. So this method is actually similar to radial acceleration relation in rotationally supported galaxies. Actually, I have been working on rotation curves for the past 3 or 4 years. So I was inspired by my work in rotation curves. So here I will present results based on stacked velocity profile test and the acceleration plane test. And I'll focus on comparing data with Newtonian prediction that can be most accurately and reliably calculated. And I'll just use generic the trend of MOND to check whether my comparison with the Newtonian prediction agrees with the MOND prediction or not. Now our discuss issues about data quality. The key measured quantity is the projected relative velocity, as I mentioned already. And this quantity comes from proper motions. So proper motions must be precise. Otherwise, you can't measure this difference. Basically, the projected velocity comes from differences of proper motions. So if proper motions have large uncertainties, then the difference would be meaningless. So that's why we require this good precision for these proper motions. And also, it is desirable to have a sufficient signal to noise on this projected velocity itself. So we can estimate the uncertainty of this projected velocity, and then that velocity need to have a reasonable signal to noise, which are the case for actually Gaia data. Okay, so now for the V tilde distribution test, a quality control of V tilde is also additionally required. Okay, but for the velocity profile test or acceleration plane test, actually these two requirements should be fine. Now, we also have important issue about undetected close companions, hierarchical systems. So they are apparent binary, but it can have undetected, hidden close companion. So how to deal with this hidden close companion? That's a very important part of this test. So one can try two philosophies. One philosophy is that we can try to remove all hierarchical systems at the cost of losing statistical power. So this is one option. Another option is we just live with hidden companions, and then we try to model them as accurately as possible. Okay, I'll define the F multi. That's the number of systems with hidden companions over all apparent binaries. So if it is 0.5, that means half of apparent binaries in the sample have actually hidden close companions. Okay, from nearby surveys, we know F multi has to be between 0.25 or 0.5, somewhere around here, but it has large uncertainty. So it is imperative to self-calibrate F multi if a general sample is used. It is particularly so because this F multi, this value depends on how the sample is defined. So if you don't pay too much, if you don't pay attention to this calibration, then your result is not reliable at all. Let me see. I have one chatting here.
Yeah, you go ahead, please. We'll take the chat later.
Okay. So I think it is not difficult to understand this point, right? Okay. So then the issue is how can one do the self-calibration? One can do by requiring Newtonian regime data to agree with the Newtonian prediction. As I emphasized already, we know that certain regime must satisfy Newtonian dynamics. So we can use those data to calibrate F multi. Now, for the first approach, can a sample of pure binaries be selected? Well, it will be difficult, but it is possible. But we'll lose a lot of blood because if the expected fraction is 50%, if you apply very strict cut, then you may end up with less than 10%. So you'll shed a lot of blood, but it is still possible. So okay. So in the specific sample I'm using, resolved companions can be identified and removed, as in El Badriadel. So the issue is how to remove unresolved companions. Well, we have some observational hint. The idea is that unresolved companions will cause oscillometric wobbling, also kinematic noise. So we can apply some Gaia Rui values and the fractional errors in proper motions and parallaxes. Kinematic noise applies to proper motions, and also radial velocities. Okay, and not all Gaia binaries have radial velocities, but we can use only those systems having radial velocities. So as I said, in this approach, we shed a lot of blood. Okay, empirically, I find that if we apply Rui is less than 1.2. By the way, Rui is similar to reduced chi-squared. Okay, so if it is around 1, it means the fitting solution is very good. So no noise. Now, fractional errors of proper motion and parallaxes less than certain value. And I find that if epsilon is less than 0.05, then it's good. And also fractional errors of radial velocities less than 0.2. These strict criteria leave less than 10% out of actually binaries that already excluded some noise. Okay, so as I said, we are just left with just a small number of cases. Then how can you know this sample is actually pure binary sample? Okay, I'll get back to this later. Okay, and what this work is not about is that it has nothing to do with dark matter, because even if it exists in galaxies, it cannot affect binary internal dynamics. Also, it has nothing to do with how binaries were formed. We are just observing binaries that are gravitationally bound, and then we just test gravity at low acceleration. Okay, now I'll describe database. Okay, so that was a very long introduction. As I said at the beginning, the introduction seems important for this talk because there are so many issues. That's why. Now, okay, now I'll accelerate a little bit. So Gaia provides accurate, precise and accurate proper motion and distances. It gives sky projected velocities, and also they provide radial velocities for some fraction of systems. I take binary samples from L-Body radar because they estimate chance alignment probability. Also, they remove the resolved companions already. Okay, so they basically select, they have some initial selection, and then they remove clusters, background pairs, and resolved triples. And also they remove pairs where the projected velocity is too large, less than 5 kilometers per second, because this is extremely unlikely. But this sample may include chance alignment cases. So this basic sample is 1.8 million binaries. So if we plot the data points in this projected velocity versus separation plane, then as I said, it includes chance alignment cases. In this, chance alignment probability increases at larger separation. And it also includes some hidden close companions, because the red dashed line, it is a Newtonian prediction when the total mass is 5 solar mass. 5 solar mass is a very large value. So any binaries obeying Newtonian dynamics or MOND, they are not likely to go across this line. But you see, there are many. So actually, there are some chance alignment and also some issues. Okay, now the main part of L-body radar is they actually pay a lot of attention to estimate chance alignment probability. So they use 7 criteria, and then they devise certain method to actually estimate chance alignment probability for each system. And as you see, when they when you see the sample distribution, then you see that at larger separation, this chance alignment probability is higher. So if you clean the sample, then you can see that at larger separation, actually the number of system drops. Okay, so I'm basically using their results as some way of cutting out unlikely genuine binary systems. Okay, so selection strategy is exclude false binaries as thoroughly as possible, and use only the most reliable data as long as number statistics is enough. And also include smaller separation binaries for self-calibration purpose. Also, I require the precision for proper motions. Okay, so these are the color magnitude diagram, the color versus the magnitude. The magnitude will give the magnitude correspond to luminosities, and they will give masses, mass estimates based on luminosity mass relation. Now, here I show the uncertainties of distances, parallaxes, and also uncertainties of proper motions as a function of a distance of the systems. And as you see, we have significant number of systems with very good precision. Here, -2 means precision better than 0.01. So you see, even there are systems with -3. So we have many very precise proper motions. So also we have some questionable proper motions. So I try various samples by trying different cuts. Here, 2 examples are shown. Also, just recently, Banik et al. Suggested the kinematic cut based on the uncertainty of V tilde. As I said in the introduction, this directly applies to their method. But in my method, I'm directly testing this projected velocity, also the inverted velocity that transform to acceleration. So in my case, this the additional criterion is not necessary. But anyway, if I check the sample, then you can see that 20 some percent actually don't satisfy their this V tilde error cut. But I can see that most of the data actually have good signal to noise for projected velocity itself. Okay, so signal to noise is better than 2 most of the data. And now I'm also showing the more precise data. proper motion relative error is smaller than this, and also radial velocity have small relative error. Then in this cleaner sample, you can see both kinematic costs are automatically satisfied. So I'm basically using various samples, not just one sample. As I emphasized, if a value or inference should be valid, that should not depend on just one specific sample. The result, the conclusion should not depend on how you define the sample. So I'm trying various samples. Now, we also need to take into account dust extinction. Okay, so this shows the distribution of individual masses and summed masses for the main sample. And this shows distribution of total mass as a function of separation. You can see in my sample, most of the systems have mass less than 2. The total mass less than 2. But this doesn't include hidden close companions, but hidden close companions cannot have mass larger than the host companion. So we expect actually mass less than 5. So, okay. Now, with some this if we limit, if we cut out these chance alignment cases using L-Badr-Adair chance alignment parameter, then actually we see that most of all of chance alignment cases were removed, and most of these above this line are removed. As I said, this line is set by 5 solar mass. So for this sample with mass less than 2, it is very reasonable. But some still can cross this red line. That shows, some for some systems close to here, if they have close companions, then they can cross this line. Now, if I show the profile of projected velocity as a function of separation, and then if I compare the observed one with Newtonian prediction, then in all bins, it's larger than Newtonian prediction. Okay, so it means there are actually significant amount of hidden close companions at work. Okay. Now, this one shows the distribution of measured radial velocities. 37% of the binaries have radial velocity. So I can use these radial velocities to select even cleaner sample, or source sample. So as you see, the radial velocities have large uncertainties. Yeah, they have large uncertainties. Only a very small number of systems can have precision comparable to proper motions. That's why radial velocities cannot be used to test gravity, but they can be used to check the binary system is really gravitationally bounded system, because if it is really gravitationally bounded system, then two stars will move at the same speed, at the same velocity in space. So I did some check, and then the samples based on L-boundary error, chance alignment probability, and the samples based on this radial velocity requirement, they agree. As you see, two histograms are almost identical. So that shows that chance alignment, the selection based on chance alignment probability and are reasonable. Now, because we want to test gravity at in the MOND regime, where we are not sure it will be Mondian or Newtonian, we must know masses. If you are uncertain about gravity and mass at the same time, then you can't decide anything. So for smaller separation systems, we are sure, we are 100% certain that it should satisfy Newtonian dynamics. So we can use Newtonian dynamics to measure masses. But in the MOND regime, we are not sure, because that's what we want to test. So in this case, we have to estimate masses using a scaling relation that was derived from these smaller separation systems. So we use luminosity mass relation or magnitude mass relation. Okay, so actually the science community agree about this. If you ask the experts, then they will point to you these results are most reasonable. But one can try some uncertainty. Also, in this relation, the masses were determined using closed binaries. So they are very reliable. Now I'll describe results. Okay, so I'll first describe results based on acceleration plane test that was published this summer. So we calculate the observed acceleration and also calculate Newtonian predict acceleration as a function of Newtonian circular the gravitational acceleration, the centripetal acceleration, and then compare these two. Okay, so there are some typical mathematics for Keplerian orbits because this is the prediction based on Newtonian calculation. So we can use textbook, the equations. And this one shows how this the acceleration ratio varies as a function of eccentricity. At large eccentricity, it has a huge range. For circular orbits, they are the same. But as you see, as eccentricity increases, the range becomes larger, and also the median decreases monotonically. So okay, these are the eccentricity distribution estimated by Hwang et al. So they use the angle between the relative position vector and the relative proper motion vector. So they can estimate the range of eccentricity for each system. So these individual ranges are actually valuable. And one good thing about using L-boundary sample is that we can use this Hwang et al. results. And also we can ignore these individual ranges, but we can just try statistical eccentricities. But this is more informative. So now I'll skip basically mathematics. So for each Monte Carlo reconstruction, one can obtain any point just out of this. This is for circular case, and this is for elliptical orbit. So we need to look at this one, the right one. So for elliptical orbits, if we do the Monte Carlo reconstruction for one system, it will be just any one of these points. So it is meaningless. You can't do anything. So with individual system, there is no hope testing gravity or whatsoever. But if we have thousands or tens of thousands of systems, then this Monte Carlo deprojection process will average out. Okay, the inclination range and the eccentricity range, that will average out, and then we can have probability distribution. Okay, that's the main idea. So these points are actually showing probability distribution from one Monte Carlo deprojection. So individual point is meaningless, as I said, but we can do some binning in this plane, and then in each bin, actually it has some probability distribution, and then we can compare the observed probability distribution with the Newtonian predicted probability distribution. And then if you do Monte Carlo many times, then you can obtain, for example, the distribution of median. And then you can compare this with certain gravity prediction. Okay, I'll skip mathematics. Now, when there are hidden companions, then one has to use the observed scaling relations. So how to self-calibrate F-multi? This is the key issue. So surveys, nearby surveys show that F-multi does not depend much on the period of binaries or separation. So we can anchor, fix this value with the Newtonian regime data, then that will be good. So basically, we can have Newtonian regime data with, for example, 500 astronomical unit, and also we can have 10,000 astronomical unit. So we can use these systems to fix the F-multi. So these processes are rather complex, although actually straightforward. Yeah, each step is straightforward, but many straightforward steps are connected, then they look formidable. But it's not formidable, actually. Yeah, I did it for several months. So anyone who want to check this, then you can use the course. I wanted to be very transparent about my test from the start, because we are talking about science, not something political or anything. So that's why transparency is a key concept in my test here. Now the results. So I produced some mock data, basically replacing observed proper motions with Newtonian predicted proper motions. Then with some 4,000 sample, I could do with a larger sample, but I didn't do that recently. So if you do some tests, then you expect near perfect match or some deviation. This is typical deviation, but in very rare cases, then you could have some deviation upward or downward. Now, I'm showing now the real result. Okay, this is from one Monte Carlo for 26,000 systems. Then in this case, you can see the medians are different. So in this case, I used this bin to calibrate the F multi. So these 2 points are matched by bearing F multi. And then these 2 points do not match, they deviate. Now, I'm showing just deviation and do many Monte Carlo. Then whenever you do Monte Carlo, you will get different points. And the distribution of this, you can obtain distribution of this difference. And then now at this point, you can compare this deviation with the specific generic prediction of MOND. And here, the fitted value of F multi is 0.48 and 0.36 that are very reasonably compared with the observational values. Okay, now if we apply this some additional kinematic cut, then the trend still remains, but the F multi value becomes somewhat smaller because some kinematic noise are removed. And in this case, further the F multi are further lower, but the gravitational anomalies remain. Okay, now this one has many bins. So if you calibrate F multi with this bin, then these 2 bins are automatically satisfied by Newtonian prediction. So that should, if this method should be correct, then if you calibrate one Newtonian point, then all the other Newtonian points must follow Newtonian. So this is good. Okay, so I'm running out of time. So now I'll show the stacked velocity profiles for pure binaries.
You could take a few extra minutes. That's not a problem.
Oh, okay. So, for this sample, we have just 2,400 binaries, and this shows mass distribution and how total mass scales with the separation. And they are very clean samples. So they automatically satisfy whatever kinematic cuts you may want to apply. So in this case, no free parameter at all. You will see that without F multi, it automatically satisfies Newtonian dynamics at small separation. So F multi is 0, it's never fitted, try to be fitted. So basically, you just calculate within the ranges of uncertainties and also the possible ranges of inclination and eccentricities, etc. Then you see in the Newtonian regime, it automatically set Newtonian prediction is automatically satisfied. Now deviation is the same for the general sample. How can this happen? Okay, now I'm showing with stricter precision. So this is for certain precision. Now I'm actually, in this case, I'm increasing the precision by a factor of 2. So the sample size is just a factor, the sample size also is just 1/2, but the trend remains the same. Now, some people criticize me using individual eccentricities. I don't understand why they criticize. You know, individual eccentricities are more informative. If individual eccentricities are not available, then you have to use statistical eccentricity. So I take their criticism. So I did the analysis with the statistical eccentricities. Then the signal is somewhat weakened, but I can see some still, it is more better matching with aqua prediction. Now I'm using many bins. Once again, here there are no free parameters at all, no fitting at all. Just you calculate, measure the quantities with the Monte Carlo method. And then you see 3 bins automatically match Newtonian prediction exactly in the regime they should. Now they deviate from Newtonian prediction following equal rather accurately. This is with the individual eccentricity, and this one is for statistical eccentricities. Again, signal is somewhat weakened. Also, the sample size is now just 2,600, so the uncertainties are large. So one can calculate this gravitational boost factor for this MOND regime. Then it is about 1.4 or 1.5. Now I'm showing the method 1, the stacked velocity profile test. So it will work when the median total mass does not vary with separation very much. So in this case, again, no free parameters at all. And in this case, there is no deprojection to 3D space. So the calculations are simpler and more straightforward. And then you see the first 3 bins agree with the Newtonian prediction without any adjustment whatsoever. Now you see it starts to deviate in the transition regime, and it agree with the MOND in the Newtonian regime. And what's nice also about this is that, as I said, under the external field effect, we are expecting a quasi-Newtonian regime. I mean, Newtonian regime with rescaled gravitational constant. So it has to be also Newtonian. The slope has to be the same, and it looks like so. And the significance is 5 sigma here. The deviation of these 3 bins altogether. Now with the different mass magnitude relation, and I'm narrowing the mass range to make sure the total mass doesn't vary with the separation, then the results are the same. Now, this one is just a half size with twice precision. Then you see no difference. So if you increase precision by a factor of 2, then your sample size decreased to 1/2, but still you have the same result. just the statistical uncertainties are large. Now this is with the statistical eccentricities, and in this stacked velocity profile test, I find that even with statistical eccentricities, the deviation is 4 sigma significant, and so it is only slightly weakened. It was 1.5, now it is 1.15, but still significant. Okay, so this is the summary. It ranges from 1.15 to 1.25. So it is what's predicted by MOND. Now I'm doing auxiliary or additional analysis with some pre-parameter to fit the higher the larger separation bin. Then if you use if you introduce hierarchical systems to match the larger separation cases, larger separation bins, by assuming that Newtonian dynamics should hold, and then this boost is due to the close companions, then you can fit these bins with the Newtonian prediction, then you cannot fit this smaller separation. So it doesn't make sense, because these smaller separation bins should agree with Newton better than this larger separation. So that means these hidden close companions are unlikely to be responsible for this trend. Of course, one can argue that only these systems have hierarchical systems. So only here we have about 300 systems here, 300 systems. So one can argue 150 out of 300 systems probably have hidden close companions. But here we have, say, 2,000 systems, but 2,000 systems don't have any hidden close companions. One could argue that, but I don't think that's likely, because these systems and these systems were selected with the same strict criteria. Okay, now one can do the test with pseudo-Newtonian. Then if you want to fit pseudo-Newtonian data, then you don't fit Newtonian data. Okay, I'm also using 40 systems with exceptionally precise radial velocities. In this case, one can measure the 3D velocity directly, because projected velocity and the radial velocities are accurate enough. And even in this case, you expect, you are seeing deviation. So one can argue that the magnitude, luminosities may not be so accurate. So I'm trying plus minus some magnitude, systematic shift. Then if you try to match this larger separation with the systematic shift of magnitude, then your lower separation system start to deviate from Newtonian prediction. So it's not good. This one is I'm trying to test perspective effect. You know, what we measure angular motion, but what we want the linear motion. So if this separation over distance ratio is large, then it could matter, but I don't think it's matter here. So I'm requiring some strict criteria. So in this case, you are basically throwing away systems with a separation greater than about 10 kilo AU. initially it was up to 30 kilo AU. Then in this case, you still the same trend in the highest acceleration bin at the right separation. Now, I think you have questions about this comparison between results. So I'll describe some comparison with other results. So why Pitodis and Sutherland and Barney-Gedel failed to obtain the MOND signal? That seems so clear and obvious from my two papers. Okay, the main problem I have is that they didn't care much about self-calibration of FMRT. So Pitodis and Sutherland used the systems separation larger than 5 kilo AU, so entirely MOND regime. And then they try to compare V tilde distribution between Newtonian prediction and MOND prediction. So and FMRT is free parameter. So you know, you try to measure, you try to test gravity, but in a sense you don't know mass, because FMRT you know, affects the total mass. So if you do not fix or calibrate FMRT, you cannot test gravity. How can? It's impossible. I mean, it doesn't matter what statistical method you use. It's about basic of science. Now, Benick et al. Went down to 2 kilo AU, but they still didn't use Newtonian regime. And actually, we had some discussion in St. Andrews this June. And actually, they agreed they will include data with less than 2 kilo AU, but they chose not to. So we, myself and some other people are disappointed about that. And Benick et al. Obtained 0.7 for their best fit model. So have you ever seen any value larger this from my surveys or my fitted values? I have never obtained this large value. So it seems impossible to me. Yeah. And also they define some likelihood, and they seem to emphasize this Markov chain Monte Carlo method. You know, I have been using MCMC for rotation curves for many years and for some other ones. Here, although I don't particularly mention MCMC or anything like that, I'm basically using the Monte Carlo method, and I'm taking into account all the possible ranges. Okay, so, and they seem to define some gravity parameter, and I'm not sure how it can be constrained so well when you don't have this calibration data. Now, why do I think so? Look at this data. You know, most of their data are in the transition region, and they have very few data in the MOND region. And then when they define the likelihood or some probability, I think each system will contribute equally. So I'm not sure how they did it. Actually, I got their sample from Indrania, and then I'm working on it. And actually, the sample is not, I mean, so good from my point of view. Anyway, this figure is from their paper, and they show these four bins in the sky projected separation. And in the near Newton regime, 2 to 3 kilo AU, so it's closer to Newtonian regime than MOND regime. So Newton preferred. Now, this 5 to 12 kilo AU, this is MOND regime. Actually, MOND is preferred, as you see. Yeah, as you see, the blue line agrees better with the data. Now, this one, 3 to 5, basically transition regime, no preference, just from appearance, but there are some statistical method may give different result. Now, this last bin, too uncertain. Data points are not large, so uncertainty are large. Also, they have checked with this smaller value of FCB. They call it F closed binary. So 0.3. I think probably referee asked them to try this. I'm not referee, or I don't know who the referee is, because this is more reasonable value. And then with this value, actually, Newtonian model is excluded at more than 2 sigma, just from blue curve. You know, 0 is excluded. And also there are many issues here because they define, so just from their definition, but alpha value is still closer to 0 than 1. But what is the meaning of 1? You know, they defined with some Q-MOND model that's actually different from equal, or a little higher than equal. And also, they did some specific set of orbit calculation based on specific assumptions, including eccentricities. And they used, of course, statistical eccentricities because they don't have individual eccentricities, because they use different sample. So actually, to me, they argued that they excluded MOND at 16 sigma. Wow, that's a great discovery. So there are many other issues with Banniger there. By the way, until a year ago, Indranil and I were good friends. Maybe still good friends, except for this issue. And Indranil is much younger than me, so I was actually helping him last year. But you know, at some point we couldn't agree each other. So unfortunately I had to do this work myself with as I said, method 3. That's a whole new method inspired from rotation curve studies. Okay, so what are other issues? They did not consider more reliable subsample. You know, they have just one sample and they are just happy with that. They don't consider reliable subsample. You know, as you have seen in my case, I tried so many samples because if the result should be robust, then it should not depend on how you select a certain sample. And also their sample includes flybys. Actually, I was trying to try their sample, and then I saw this flyby issue. So I stopped for the moment because, you know, whenever flybys are there, it basically creates huge amounts of kinematic noise. So if you cannot remove flybys, then you have to work with them. But if you can, why not remove them? I don't understand their logic. I mean, Pitodis and Sutherland included flybys, and Banniger still include flybys, although they can be removed completely. If they require to have same radial velocities, then, you know, if they have same radial velocities, then they must be gravitationally bound system. It can't be flyby. Yeah. So they don't do that. I don't understand. Okay. So now I would like to emphasize that now my new paper, the title starts with robust evidence. It shows even if I use statistical eccentricities, so deliberately dilute information, I still get gravitational anomaly. Yeah, unlike Benny-Gadel, Hernandez and Hernandez et al. Actually obtained results consistent with my results. Actually, until last year, Hernandez actually obtained somewhat different from this, actually somewhat higher than this. But with Gaia DR3, now they have results agreeing with mine completely. So my results and Hernandez's results, I mean, he used completely different sampling. He doesn't use El-Badri sample. So we use different samples and different codes, but we basically confirm each other. Now, these are the most recent results. So for small separation, it agrees with Newton, as you see. Now for larger separation, it agrees with MOND. So as I showed you many different results with two different methods, wide binaries seem to show an immovable gravitational anomaly in an acceleration-dependent manner. That's what exactly predicted by MOND. I think this is amazing. Okay, so we have to wait until data release 4 comes out, but until then, we have 2 years. So if one can measure radial velocities for some of some of systems in the sample, then I think they will be useful. So it seems that general relativity, despite all its successes outside the MOND regime, seems valid only outside the MOND regime. So they, if these results are correct, then that means general relativity must be broken down because it's a non-relativistic limit agrees with the Newtonian prediction. And also, standard cosmology is based on general relativity, so that's also questioned. And MOND-based cosmology that has been discussed for decades actually, and now is well motivated and much needed. So if we take these results, then this is what the data say. A paradigm shift seems on the way. So I think a good news for theoretical physicists and mathematicians. So I think that's why you invited me to hear about this result. Okay, so this is my last slide.
Yeah,
okay,
great. Thank you. Thank you so much for a great talk. Very clear and very inspiring. And although I'm a theorist, I could get a good feel for what you're doing. Thank you very much. The talk is now open for questions and discussion. Kindly use the raise hand icon to please ask your question. Maybe just to get the discussion going, I would like to invite Professor Hernandez to tell us a little bit about his work and comparison. It's very interesting to know that both Q and you are getting the same conclusions. Could you please tell us about your work? We'll hear you next year, of course, but this is, I think, a good time also to know your view on Barnick et al. And your comparison with Q's work. Are you there, Xavier?
Yes, I'm here. I'm here.
Yeah, please go ahead. Welcome. Good
Thank
to
you.
have
Thank you very much. Well, I mean, I think there are a number of issues that Q has just raised regarding, for example, how changing the sample keeps the results constant, how changing the method keeps the result constant. He did mention that my sample, the sample I use and the sample he uses are consistent or yield consistent results, even though we use very, very different methods, in fact. I do not do this 3D projection. In the first paper of mine that he cited, I just used this as stacking business, basically just checking the relative velocities as a function of separation, and I also get a very clear signal for Newtonian, perfectly consistent with Newtonian dynamics in the small separation. This is not a trivial result because Newtonian dynamics have never been tested out to, say, 2000 astronomical units. No, Newtonian dynamics has been tested in the solar system with exquisite precision, and in tight binaries as well, reaching, say, tens of astronomical units, but never out to hundreds and even thousands of astronomical units. And without any free parameters, we reproduce precisely Newtonian expectations. Now, the main result, the zero order result of both my results and Q's, is for a transition at 2000 AU for, say, solar mass or a little below solar mass wide binaries. And it is very hard. I think it doesn't make much sense to try and either prove or disprove these results if you look only at the larger than 2000 AU separation regime. So if we're finding evidence for a transition at 2000 AU, the only reasonable way of checking this, one way or another, is to compare, is to have a study that covers both the near and the wide binary sample, and that hasn't been done by Barnick et al., for example, or by anyone else. So maybe we're wrong, but if we're wrong, then you certainly have to show that there is no transition between the near and the far regimes, and that has not been tested. As Q just mentioned, if you look at a dirty sample or a sort of a sample, a very large sample, you get high statistics, but necessarily you are dealing with a very mixed bag of things. No, so you have the binaries, but you also have the binaries with the near companions, and you also have flybys. And also, for example, in the very wide binary samples, you are already looking at things, for example, in the Barnick sample, in the widest sample, he goes all the way out to 30,000 astronomical units. I stop at a little over 1,000 or 1,000 or 1,500 or something like that, because the widest samples cannot be guaranteed to be isolated, okay? As you go to wider and wider binaries, the chances of having some other stuff around grow significantly. And these are very tenuously bound systems. They are not tightly bound systems. So if you have another interloper 3 times or 2 times the separation of your wide binary around, that can influence the internal dynamics and mess things up. So, I mean, I have taken an extreme view in that in the studies I do, I always try to make sure that the binaries I'm using are genuine binaries and completely free of hidden tertiaries. So my samples are extremely small by these standards, but yet much smaller than Q's even. And that's why my statistical significance levels are much lower, but they are perfectly consistent. So I mean, also there's the point, if you want to look at these results, mine and Q's, as an artifact of signal to noise or hidden tertiaries, etc., then you have to answer why on earth is this kicking in exactly in the regime where multi-milgram predicted 40 years ago, and exactly with the right amplitude, and exactly at the right scale, no, and with exactly the right radial dependence. Sorry about that. So, so in any case, I don't think this. It is very hard to think of this as a coincidence. I think, no. That's basically what I can say at the moment.
Thank you. I just wanted to ask both you and Kyu two questions. So, do Banik et al. Have an explanation or a reason why they are not considering the closed separations binaries in this? I mean, they don't say anything.
Well, I mean, as Kyu said, we sat down and talked about it and say, well, you know, perhaps we're wrong. If we're wrong, the faster we find out that we are wrong, the better, no? And stop wasting our time. So please check whether there is a change of regime or not. So please take a look at the narrow regime. I think the answer is that Banik's method is extremely time-consuming and extremely computer-wise very expensive. So it takes too long to run if you include the narrow binaries or something like that. And then they have a broader range of masses, which obviously confuses everything because the signal is less clear. You're mixing up things with different with a wider range of masses, but having slightly larger masses, that also means you have a few smaller, well, the larger masses are more Newtonian at a certain separation. So it's all mixed up, but they think that maybe since they include larger masses as well, even though it's in a completely mixed up manner, that guarantees that you have some Newtonian signal there. And some systems which are in the Newtonian side of the transition. Not clearly, no. I mean, I think it's an important issue. I think the most reasonable thing is doing things like what Kyu just showed. You restrict yourself to a narrow range of masses so that you are isolating the effect you're looking for, and then you change and then you check both sides of the predicted transition and see if you see a transition or not.
Can I go to the bathroom?
No, yes, you can go to the bathroom.
Okay. And suppose if you ask them to take the Al-Badri data, do whatever they want to do with it, and let's see what they get. This also must have been suggested to them. Take the various Al-Badri samples that Kyu has taken. Let Banik et al. Also take them, and let's see what they get. So this has not been done yet, is it?
No. We actually suggested that they should take a similar sample and explore what happens when you look at both sides of the transition we find. And they said yes, we'll do it, but then they didn't. They've just published results for what happens if you only look at the wide binaries. And as Kyu has explained clearly, there's a fundamental physical reason why wide binaries, any changes of gravity, any presence of hidden tertiaries, and any presence of other contaminants such as flybys are degenerate. No, you can't possibly get rid of those degeneracies because the velocity at which these two stars will be moving depends not only of gravity, but also on the presence of a hidden tertiary, also on the fact that some are unbound and are just flybys. You cannot get rid of that. So I mean, Kyu gets rid of that degeneracy by looking at by calibrating this hidden tertiary fraction in the tight binaries. So then he knows how many you have there. It is important to notice that these binaries are so wide, even at the end of the Newtonian regime, that formation of the tight binary of the hidden tertiary it becomes independent of the distance. So that's why direct searches for these hidden tertiaries have confirmed that there is no observed dependence of the hidden tertiary fraction, say from 1,000 AU to 10,000 AU. No? They're all, even the closer ones are already so far away that whether you have a tight binary or not, a tight hidden tertiary or not, it does not depend on whether the other wide companion is at 1,000 AU or at 10,000 AU or whatever. No. So yes, I mean, I think we were actually expecting, very anxious to see what Banach results would be once they included the narrow binaries, but they, for some strange reason that I fail to understand, decided not to.
Yeah, because I remember reading the discussions in Stacy Maggar's blog just after the June St. Andrews meeting, and it was written there that Banach et al. Agree to do the narrow binaries and will come up with new results. So yes, it was surprising to see that. Q, you have some more response to that?
One reason Banach provides not using L-Badr sample is this figure. So this figure shows that the data points don't cross this red line. So most of the data points are below this red line, and he claims that this is the problem. So that's why he can't trust L-Badr sample. So that's actually a strange reason, because as I said here, without hidden companions, total mass is less than 2. So this is based on mass of 5. So whether in Newtonian dynamics or MOND, maybe in some extremely, without external field effect, some strange gravity theory, it may not be suitable, but for testing MOND, I mean, there's no problem. And also, I didn't apply this red line to cut out data. Actually, some data points actually cross. Cross red line. So there are no problem here. I didn't use this curve. So actually, maybe because his sample goes to larger mass. His sample goes to larger mass than mine. Here. His sample. Not this. This one is mass.
Also, just a brief comment. This point that Q is making at the moment is independent of the separation, so it doesn't preclude one from using narrower binaries as well. I really don't know why they have decided not to include the narrow binaries.
They're just out of my curiosity. Apart from these 3 groups, you two and Banach et al., are there more people now and doing this DR3 analysis?
There's a group in London that includes basically Will Sutherland and Pitoridis Charalambous, who have the last thing they published started at 5,000 AU, so way into the Mondian region. The Mondian region, as Q and I have found, starts at 2,000 AU. So the last result from the London group started at 5,000 AU, more than twice. So again, with no chance to calibrate the hidden tertiaries or to sort of try to get a handle on restricting the degeneracies because they were only in the Mondian regime. They didn't have the Newtonian bedrock to sort of calibrate. Two interesting points regarding this other group. One is that they are both two of their members, their main members are also authors in the latest Banach paper. But although I haven't heard from them directly. And another interesting point is that the main researcher in that group, Will Sutherland, was the referee of my latest paper, and was very encouraging and very supportive of my latest results as a referee. He actually made himself public, and if you look at my latest paper, we've got a thanks, an acknowledgement to the referee, who identified himself as Will Sutherland. So I don't know exactly what that means one way or the other. No?
Are you saying that, can you say that in the Banach et al. Paper, Sutherland is contradicting his support for your results?
Well, I'm saying that he's he on the one hand certainly refereed my paper very positively, where I show a modest, let's say, 2.5 or something sigma result in favor of MOND and essentially falsification of the Newtonian prediction in that regime. Whilst he's also part of this Banach paper where they claim a 19 sigma exclusion of MOND. Now, looking at the graphs from that same paper, and look which Q is showing us right now, the figure that's on his screen at the moment, you can see a Newtonian preferred region in the transition, a very confused situation in the 3 to 5 kilo AU, a clear preference for MOND. You see the black line is above the Newtonian black line is inconsistent with the observed distribution, which beautifully agrees with the MOND prediction, and then a very wide sample from 12 to 30 kilo AU, which is full of interlopers. I would trust. That's why I always end my samples at 12 kilo AU, because beyond 12 kilo AU, you cannot be sure that there are no external perturbers around. Not only flybys, but also things where you have external perturbers. That is too uncertain. Looking at those four graphs we're seeing right now, I don't see how you can end up with a 19 sigma exclusion of one or the other. No, I mean, looking at those error bars and looking at those plots and histograms, it's obvious that one way or the other, there's no exclusion beyond 2 or 3 sigma. No, at least to my I don't know. That's how those four graphs look to me.
Thank you.
So I'm very suspicious of this 19 sigma business that they claim.
Also, more general, just for my understanding, the equal MOND model that you confirm here is the same model that does very well with rotation curves in our galaxies.
Yes,
I think you should answer that, just because he's done much more work on rotation curves than me. Yes.
Yes, exactly. Yeah, so I got results that agree with the galaxies very well from recently. And when Indrahanil said to me last year that he got this 19 sigma ruling out aqua or Q-MOND and this modified gravity, I was very surprised, because I was obtaining results from galaxies that agree with aqua so well. So I was initially disappointed, but I thought that, binary results are directive results, and the galaxy results are less directive or indirective or circumstantial, just like dark matter. We don't have direct evidence for dark matter, but if there direct evidence comes out, then direct evidence should override indirect evidence. That's why I was serious, but I had to acknowledge the data. So initially I trusted the result, and then I was even thinking, oh, now it's time for me to come back to general relativity. So just my regular research. That's what I initially thought, because I thought Indrani would have done everything correctly. But just as a helper or a co-author, it was very difficult for me to judge what he did wrong and what he did correctly. And if I ask questions, the answers were not satisfactory. And then I just tried to do some basic sanity check of his data. And then, my gut feeling told me, oh, these results can't be right. So I told him many times, your results of, say, 20 sigma or 16 sigma, whatever, that can't be correct. So I told him many times. And then, we started to, go this opposite ways. And then, I still had a lot of work to do in galaxies, but, for me, it was a big deal. Whether I'm going to back to general relativity or stay doing some more work in MOND related, doing some MOND related. So I stopped everything about galaxies, and then I started to think about this problem because it was a big deal for me.
Definitely, thank you. And do you think DR4 would help more, or we already have clear conclusions? Would you say that DR4 is not so critical at this stage? What's your view on that?
You mean
Gaia DR4 2025? The next release, will that help us improve?
okay. I'm not sure about the details. Maybe Javier can tell more the details of DR4.
Well, as you see, Q presented two main ways of looking at the problem. One is to have huge samples where you have to somehow model out kinematic contaminants such as hidden tertiaries and so on. And the other is constructing extremely pure samples where you essentially get rid of those hidden tertiaries through a number of astronomical exclusion cuts. Now, DR4 is going to have, for example, many more radial velocities. So not only parallaxes, but radial velocities to each of the stars. So right now, that is one of the limiting factors in reducing, for example, my extremely clean samples to very few stars. So in DR4, there's going to be more radial velocities, and that's going to make a difference more in terms of the small clean samples. The large samples are already large enough. Now you already have 20,000 stars or binary stars or whatever. Of course, they're full of hidden tertiaries and flybys and so on. But if you want a very clean sample, then you need, for example, radial velocities to both stars to exclude flybys and so on. So my flyby, my very clean samples are going to get a little larger with DR4 and DR5. Right now, I'm claiming something like a 2.5 sigma result. Q is claiming a sort of 5 sigma exclusion of Newtonian gravity with his clean samples. So yeah, I think we're going to. I think the trend is there. I mean, if we're making a mistake and we're not really ruling out Newtonian gravity, then it's a remarkable coincidence that this other kinematic contaminants come in exactly at the amplitude, exactly at the separation range, and exactly with the correct radial dependence that was predicted by MOND 40 years ago. No? But yes, I mean, that's going to be cleared up. And another point is that if we're looking at hidden tertiaries, there was a very nice paper by the London group, by precisely Will Sutherland and his collaborators, showing that these hidden tertiaries can be seen, can be found through direct follow-up. So there are observational techniques to look for these hidden tertiaries. Okay, so Q finds a deviation from Newtonian gravity in the wide binaries, and so do I. This has to be due to things like hidden tertiaries. Well, one can actually ask for telescope time and see if those hidden tertiaries are there or not. That is within the reach of current techniques. And I know that there are at least 2 or 3 observational proposals and observing follow-up programs being undertaken as we speak to see if these hidden tertiaries are there or not.
Okay, thank you. And you have mentioned earlier on that it would be great if we had, say, just 1 or 2 very clean white binaries. That would be good enough. But is there a prospect for that ever in the future? Something like Mercury's perihelion?
I mean, not with Gaia. I'm not sure about the status of future measurements, but given that the periods are so long, you really need extraordinarily precise data to make sure that you're looking at a bound system. I think this is going to remain a statistical problem for, I don't know, engineers are astonishing and they come up with astonishing ways. I mean, having started this with Hipparcos catalog, and the Hipparcos catalog 12 years ago was more than anyone 30 years ago would think possible. And now we have Gaia, which superseded Hipparcos by orders of magnitude. So I'm not going to say anything about what might or might not happen 10 or 20 years from now, but not before that. I mean, certainly with the current situation, I think things are going to remain statistical at least for another 10 years.
Now, how did your work evolve over this decade period when you moved from Hipparcos to Gaia? You have a long-term feel for what's going on here. So,
well, Q showed my initial results of more than 12 years ago, and as you see, the signal to noise there was even below 1. Now my recent results in the cleanest region for the wide binaries, the signal to noise on the final relative velocities on the plane of the sky is of more than 10, almost 20 sometimes. No, so it's been a little over an order of magnitude, order on 1.5, say, order of magnitude improvement in the signal to noise, and that's allowed. For example, in my initial results, you couldn't trace the Newtonian regime. No, you couldn't see the clear Newtonian regime, Newtonian results that as Q mentions, are non-trivial because no one had ever verified directly that Newtonian dynamics applies all the way out to these low accelerations, these separations of order 1000 AU, let's say. We didn't have the certainty that Newtonian dynamics did apply at separations of 1000 astronomical units. Now we do. So there's been a sort of 1.5 order of magnitude improvement in the measurements in the past decade or decade and a bit. Maybe the same happens over the next decade. Let's see.
Great. Thank you. Bernd, sorry to keep you waiting. Go ahead, please.
Yeah, so here
No need
in this
to say sorry, and thank you very much for the nice and interesting talk. I would have a question. You said something about a decreased Newton or effective Newtonian constant. So do you have a variation of the gravitational constant in your model or in your theory?
You mean decrease of Newton's constant?
You said something about a decrease of Newton's constant.
Oh no, I said increase. Increase.
Oh, sorry. Then okay, that doesn't change much of my question. So does the gravitational constant or Newton's constant change in your model depending on the separation of the system or something?
Yes, that's what the main result. Let's take this result, and you see it follows Newtonian prediction for smaller separation bins, and then there's a transition, and then it is again Newtonian, but with different Newton's constant.
Different Newton's constant.
Yeah,
okay,
boosted Newton's constant.
Okay.
So the slope looks the same, right?
Yes, now
And
it's okay.
so I can show also this result in more directly in acceleration space. As you see, it is Newtonian and then makes a transition and it goes again quasi-Newtonian with a different Newton's constant.
So you have a traditional Newton regime, then you have a MOND regime, and then you have a kind of enhanced Newton regime. Where
a Newtonian regime, and then transition regime, and quasi-Newtonian regime.
okay,
Quasi-Newtonian regime is the MOND regime under the external field effect.
okay. And one brief follow-up question, then the next person can ask the question. You said that you used a specific, also general relativistic MOND model, this quadratic Lagrangian theory. Are there any other models compatible with your data, or can your data also select the right kind of generalization of general relativity? So
Equal is not a general, it's not a relativistic theory.
okay.
Yeah, it is just a classical Lagrangian, so that it has a fundamental limitation. So it is just a phenomenological model, just to fit,
Okay. So
to fit the data, and there are actually theoretical investigations to develop relativistic theories, or in general to develop new theories to encompass equal and general relativity at the same time in the relevant regimes.
okay, thank you very much. Then yeah, I'm done with my questions, and the next
Thank
person
you.
can.
Thank you. More questions, please. Please go ahead. Yeah, I should please. Yeah, I'll give you the unmute. Yeah.
I think Ghazal was first. I saw her up earlier.
Yeah, Ghazal, you go ahead, please, Ghazal.
Yes, sir. Hi, Professor Q. Thank you so much for your talk. It was very informative. Sir, actually, I have a question related to your earlier publication, maybe in August month of 2023, in which when you were assigning the probability distribution to the hidden companion to the binary systems, you divided the probability like 40% to primary component, then 30% to secondary, and then another 30% to both of them. Could you please tell me how did you decide, means what number to divide into these three categories?
Oh, okay. First of all, that's a fine detail that doesn't affect the main results or conclusion. I took Reader et al. Reader et al. Did some survey, and they obtained that they measured about 200 binaries, and then they found some systems where both have the hidden components. So it doesn't matter actually, because hidden components have relatively small masses. So you can just change the number a little bit, but that wouldn't change the results. Yeah.
Okay.
Did I answer?
Sir, sir, I have actually more couple of questions. Can I ask you, sir?
Yeah. Go ahead.
Okay. Your slide number 31, in that figure.
Sorry, one.
Your slide number 31.
Oh, okay. Oh, okay.
Sir, actually, I tried to reproduce this image, the top left image. So, sir, actually, I am getting some more points below the diagonal cut. And actually, you have mentioned in the paper also that some of the systems you have excluded, like main sequence and giants and some others. So I, sir, just want to ask you that how do you decide which systems to exclude in the figure?
Oh, here. Yeah, I
Sir,
used
top left, yes.
yeah, I used this red dashed line. Yeah, I
Yes.
used
So below that dashed line, I am getting some points.
yeah, I'm not using those points in my analysis. So you're asking what's the criterion, you know? I'm using
Correct, sir.
correct. Well, this is also fine detail. Just here you see above it is you can see the scatter above is stops at some distance. So I used some criterion, but actually I discussed this with some expert, and then they seem to say it's okay to include this because the colors were probably affected by the companions. Yeah, but this is again a fine detail. It doesn't matter too much whether you include or exclude these systems. And my philosophy is that if colors, if colors are too different from main sequence, why would you want to use them? You know, in binary test, what matters is something like this: how the mass distribution varies with the separation. And also in my method, acceleration plane method, all probability distributions are here in the acceleration plane. So as I said, it was inspired by a radial acceleration relation of galaxies. So in points like this, all these galaxies come from all different, from dwarf galaxies up to large giant spirals. Yeah, because they are in the acceleration plane, you can stack the points. So in my analysis, I just want to remove suspicious data. It wouldn't harm the analysis. But if you try to include suspicious data, then that could potentially harm your analysis. Do you see my point?
Yes.
Yeah. So excluding points below that red curve, actually, even if you exclude those points, it wouldn't, in this case, harm very much. Yeah, because they are minor. But as I said, I don't see any reason to use suspicious data. Yeah, that's basic strategy.
Okay. And sir, lastly, I want to ask you is that I have been following both of your papers, the recent publication and the previous one, which we are just talking. So, sir, you have two different approaches in both the papers. Like earlier, you actually allowed the F multi to self-calibrate itself, whereas in the recent one, you are putting F multi to be 0 in the first step. So, what would you advise to be, what would you advise us that which approach is more reliable or more preferable, or both are the same for the future work?
Oh, for the future work, I would suggest both. But remember, actually, the second analysis is not totally different from the first one, because if you use tighter and tighter criteria, then F multi decreases, right? And then this pure binary sample is just the limit of this F multi range. So it doesn't matter whether you use FMRT or sample with FMRT 0.1 or 0.2, 0.3 or 0. So I did this analysis just to show that even with this extreme sampling, the results still, stand. Yeah, that's the main point. So I wouldn't say which method is better, because in this pure binary sample you lose a lot of statistical power. So I said you shed a lot of blood. Yeah, right. So it's both good and bad. Yeah. So if you use, say, well thought out some large sample, say 30,000, then you could get easily 10,000 reliable. 10,000. I mean 10 sigma. I'm sorry. You could get 10 sigma signal, and you could defend your result is reliable and correct against all observations. So yeah, I think there are still a lot of work to be done. Yeah, even with Gaia DR3. I did 2 extreme samples, but there are in between. Also, I considered only up to 200 parsec. You can go further. And also, you can do a lot of things. Also, these dust extinction models, I used one specific model that was suggested by an expert. By the way, I consulted experts every aspect of the data because I was not in this field. And one expert suggested some specific dust model that can be found in my paper, but you could try some other dust models. The dust map I'm using has a limitation. They provide only 70% of sky. So if you have some reliable dust model that can cover 100% of sky, then you could have 30% more data than I used. Yeah. So there are issues. So the dust issue becomes important if you go to larger distance. So Bennig et al. Actually didn't correct their absolute magnitude with dust extinction. They just avoided some galactic plane on the sky, and then they didn't use dust extinction correction. But one could do better if you go a larger distance than 200 parsec, say. So if you look at all these issues carefully, there are still a lot of good works can be done, I think.
Okay.
Yep.
Thank you, sir. Thank you so much.
Thank you. You do not expect your result to be overturned by this, what you call remaining good work with DR3.
Me?
Yeah.
No.
Yeah.
No.
Yeah.
I mean, if you look at my paper, what I wrote, if I were referee of Bennig et al., I rejected it definitely, with 100%. Because, I believe my results, and their results cannot be correct. So, it's surprising that, Will Sutherland accepted Javier's results. That's that's inconsistency. If he's a co-author of Bennig's paper, I could have been co-author of his paper last year, but I declined because I didn't agree with the results. Yes. So if Will agreed with Bennig's result, then he should have rejected Javier's results, Javier's paper.
I agree.
How can you accept? If you have a 16 sigma result, but how can you accept
90
otherwise results? That's nonsense.
Yeah, Xavier, you're saying something?
No, I was just correcting Q, because I think Bennig's result is not claimed as a 16 sigma result, it's a 19 sigma result.
Yeah. And if I could ask, this Milgram has been discussed, talked to about the current situation. You probably mentioned something. He has a view on it too, right?
Well, from some I mean, Moti, he acknowledges that he's certainly not an expert on this particular problem. I mean, he I'm sure would be happy to find a direct verification of his ideas, which is what Q and I are finding, particularly in a regime where dark matter is not relevant. But he certainly acknowledges that he doesn't know the first thing about white binaries, so he's not going to make any strong claim regarding this until more people have confirmed or otherwise what we have been finding this past year.
Yeah, thank you very much. Hilary, could you kindly unmute yourself, please, and ask your question?
Hiya. Okay, first of all, I should say that I'm not an astrophysicist, and I could just have misunderstood everything. And maybe you went through this in the slides that you had to skip for time. But I'm wondering what this does to the equivalent of the Hill spheres for this system. Because I mean, when you're looking at galaxy rotation curves for galaxies outside this one, you're not in a rotating frame when you're doing those measurements. Whereas if you're looking at binaries within our galaxy, then you are. And if I've understood your results about how what you see and what MOND predicts is that the effective value of Newton's constant gets higher when you're right at the edge of when you've got very, very wide binaries that are only just bound. I think that implies that there will be systems that, from a Newtonian point of view, are unbound and must be flybys. And yet, if MOND is correct, they are bound. In which case, there should be systems that are right on the edge of the flyby set that I think you have, as I understood it, you're excluding things which are evaluated to be flybys under Newtonian mechanics, right? Some of those, right, ones that are only just flybys may not actually be flybys at all. Maybe they're actually bound. And there are orbits that are prohibited under the Newtonian model that are actually bound under MOND. And if you can find those, even if you've only got a handful, I think that will be very strong evidence. And so what I'm saying is a suggestion that maybe some of the data points that you've excluded actually contain some really strong evidence. But as I said, I'm not an astrophysicist, so I don't know how to go about that data analysis to do that.
Maybe I just quickly clarify that all this is taking place way inside the Jacobi radius of the problem. So under a Newtonian model, unbound due to unbound binaries due to the tidal field of the Milky Way, they appear at about 1.7 parsecs. So that's still about an order of magnitude or somewhat wider than even the widest binaries that Banach or Chae or Q are considering. So we're staying clear of any tidal effects. However, yes, you're right in that some of the some systems which could be unbound under Newton would be bound under MOND, and those might be interesting. But as you see, given the or some other funny model of gravity, but given the most studied expectation of standard MOND sort of theories is only for a change in gravity or effective change in Newton's constant by a factor of 40%. So, I mean, one could try it, but we're kind of trying to play safe and for example, using things like the relative velocity, the relative radial velocity, and so on, limits to exclude everything that is unbound under either Newton or MOND, we want to sort of be sure that things are that the binaries you're looking at are bound. These other cases that you mentioned, bound under MOND and not bound under Newton, would probably be swamped or would be hard to pick out from the sea of flybys and so on. No, I mean you do have a sort of background noise in terms of chance associations, and there are many stars in the galaxy. You know, they're all over the place, and you don't want to have to drop. It's easier to try and maybe later, but right now we're trying to establish the presence of a gravitational anomaly here. We want to be clear of any sort of flybys, and the idea is to try and sort of limit yourself to really binaries which you know are physical associations under any theory. No, maybe
okay.
Once this has been established, one can start to look for these extremely interesting cases that you mentioned, but they're going to be, you kind of have to pick them out of a sea of flybys. No.
Right. Okay. So yeah, I did misunderstand something. I thought we were right up against the Hill sphere boundary, right?
No,
And
no.
these things are only just bound, and so that's clearly incorrect. And I mean, thinking about it, stuff that's right out that far will be moving so slowly that determining its trajectory will be really, really hard.
Yeah.
Right.
Yeah, but that's at
Thank you.
1.7 parsecs.
Yeah. Right. Okay. Thank you.
I think what she is suggesting is don't use, for example, don't use this chance alignment probability to cut out data, and then you check whether these data have the bound by MOND. Is that correct?
Well, okay. From what Xavier was saying, I mean, what I was suggesting wasn't terribly well posed. I was assuming that these binaries that you were looking at were close to their Hill sphere with respect to the galaxy's tidal effects. But from what Xavier is saying, we're not. It's way, way further inside than that. In which case, what I'm suggesting doesn't really make sense. Right,
okay,
I don't think so. Not
I'm
from
not
what
sure.
Xavier said.
What do you mean by Hill sphere?
The tidal radius, essentially.
Oh, tidal radius. You mean Jacobi radius?
Yeah.
Oh, okay.
Yeah.
Okay.
Thank you. Lawrence, please go ahead.
Thank you. I'm also not a current astronomer. My PhD in astronomy was many decades ago. But I wanted to ask a question. There was another proposal for looking at for MOND in the solar system with the I think particularly Neptune, where it was at the gravitational saddle point. Now I did a quick calculation, and I think the gravitational saddle point for a one solar mass star and the center of the Milky Way, or the Milky Way as a whole, would be about 5,000 AU. So the question I'd ask is it actually possible to select stars that were in this region where you might expect to see an enhanced MOND effect?
You mean 5,000 from Sun?
No, I mean, in the case of I was talking about 5,000 AU between the two stars.
Two stars.
Yeah, separation of 5,000 AU.
Yeah.
We have several in that range.
Yeah. We have many binaries.
Yeah. So the question then becomes: are any of them lined up with the galactic? So with the axis between the two stars, does it line up roughly with the galactic center? Because if it did, then one of those stars would be near this saddle point, and therefore you might expect to see a bigger effect. But it's just a thought I've got, not as an expert on this.
actually I have no idea about that. Yeah.
Yeah, well, I have given some thought to this problem of orientation. Now, the thing is that I've always, from the start, just wanted to take a look at an extremely pure sample, where I'm sure I'm not looking at flybys or hidden tertiaries or etc., but I'm actually looking at gravity between 2 point sources. So that limits my sample very much so. So in the wide binaries, I end up with 100 stars, okay? Q ends up with a few hundreds or a few thousands, even maybe he could try it. But if I try to include geometric orientation selection effects, I'll end up with 0.
Yeah,
with
I
my sample,
understand
I end up
that,
with
yes.
0 binaries. Maybe Q could try it, but I'm sure with a large sample like Q's, something like that could be tried and see if cutting it by orientation, maybe something comes up. I have no idea.
Yeah,
Could be tried.
as I said, just until a year ago, I was working on, working with the galactic data. So I was not, thinking the whole range of issues in this stellar dynamics and celestial mechanics. So I think your idea is good. Yeah, maybe someone
Well,
can try.
I hope somebody decides to take it up. It's not something I can do. I'm retired now.
Yeah, thank you. So just a slightly side question. Apart from wide binaries, are there other potential systems with the subcritical acceleration? So is, for example, these open clusters that Krupa and group studied, migration of outlying stars, is that I'd like to know from both of you your view on that system or any other potential test beds for MOND?
Yeah. Pavel Krupa's work is definitely good and interesting, and they are, I think, doing some improved work as far as I know. So some improved results will come out, and also in solar system, there's the Planet 9 hypothesis. Yeah, there's a Planet 9 hypothesis. Try to explain Planet 9 hypothesis with MOND.
Yeah,
and actually, the real issue I'm thinking about is Pioneer anomaly. Yeah, and there are some claims that this Pioneer data don't agree with the MOND. Yeah, so if I have time, I really would like to look into actually what are the real issues and how to, in one way or the other, how to understand the issue there. So right now, wide binary agree with MOND. So some people have some strong opinion that I think Indrani probably next week will emphasize this Pioneer data don't agree with MOND. So it makes more sense wide binaries also don't agree with MOND. Yeah. If you look at his paper, he should focus on wide binaries, but he brings a lot of issues and then he tries to say my wide binary results agree with those things. Yeah, so I'm interested in this actually Pioneer spacecraft data, and so also as you know, as you probably heard, the Alpha Centauri, the Proxima Centauri is well separated from the two stars, and two stars are like just a single star. So we can measure this Proxima Centauri orbit with this, not within with the current technology, but maybe in the future, maybe some with new technology, we could do some direct test with one system. Yeah.
Thank you. Thank you.
Yeah,
Xavier?
so I think that there should be many issues one can think of. So yeah.
Xavier, did you want to add anything there?
No, well, just to mention, for example, you say all other low acceleration systems. I've looked. There's been a lot of there's some literature I've part of that by myself, looking at the outskirts of globular clusters. So galactic globular clusters are fairly close by, and they have been known for decades to be extremely well suited Newtonian systems when considering only the central velocity dispersion values. But some years ago, Ricardo Scarpa started measuring the profiles of the velocity dispersion profiles of these things, the radial dependence and how the sigma of the stars in globular clusters changes with distance. And it turns out that it flattens is a bit like what happens with galaxies. It doesn't continue falling, but actually flattens. I've showed, for example, that I have a few recent papers on that issue, showing that the amplitude of the velocity dispersion in the outskirts of globular clusters correlates with their total masses, with total baryonic masses, just as the Tully-Fisher relation does. So that's some indication of MOND phenomenology in a low acceleration regime that has nothing to do with white binaries or galaxies. However, the issue there is a bit complicated because, well, there's issue. For example, there's a problem with how many whether the velocity dispersion you measure is affected or not by binary stars. They're so far away you cannot be sure that the individual stars you're measuring are actually individual stars, or if there is a boost to this velocity dispersion from undetected binaries, tight binaries, or whatever. They're much further away, so it's a much cleaner, it's a much less clean test than with the white binaries. So there's been competing explanations to that observation. It's not clear if we are looking at MOND or not in globular clusters. I mean, yes, I thought of other options as well, but yes, we are basically. I mean, Gaia did open up this white binary test significantly, as you can see, and I suppose we will be waiting around for the next satellite to see if to start looking at higher order effects, I suppose, and details, and things like yes, try to go further out and so on. But look at the plot that Q is showing us at the moment. There are many stars. The field of the solar neighborhood is absolutely teeming with all sorts of little things,
Yes.
And one has to be careful with that, not to. So yes, it becomes messy. It becomes messy when especially when you go to larger separations. The chances of interacting with some other little bit around it increase.
But suppose I made the statement that the independent analysis by you and by Q has already settled the issue in favor of MOND. Would you qualify that and say, no, I want to see something more, etc.? What would you say?
I mean, I would like to know Q's opinion on this, but my opinion would be that you can never confirm a theory. You can also only falsify it. So I would say that mine and Q's independent samples, independent work, independent statistics, and so on, show that have disproven Newtonian theory in the low acceleration regime, certainly, and they are also consistent with MOND ideas, sure, but they could be consistent with other things as well.
And I think your first statement is more important. That is what will get. So you are saying that you find it very convincing that in the low acceleration regime in wide binaries, Newtonian gravity is disproved.
I would agree with that statement, yes.
Q for
Whether that
simple
implies MOND is the absolute answer or not, I wouldn't agree with that.
I agree. Yeah, I agree with you.
Particularly, we have no definitive covariant version of MOND, so I would keep my eyes open for whatever might be around.
Yes,
No,
I agree. I agree.
Theoretical landscape is wide open, but it's certainly interesting that we're looking at a problem. It's particularly appealing or striking that it is exactly the same acceleration regime where you find the gravitational anomalies in galaxies, where you can just add dark matter. But here the velocity dispersion of the system is such that you need to add a new type of dark matter, no? That happens to appear precisely where the gravitational anomaly or gravitational scale of galaxies predicts it should appear. I mean, it's
so what you're saying is there's no a priori reason for the A naught in the wide binary system to be the same as in galaxies. Yes, absolutely. Yes, I agree. Yeah.
I don't know what Q has to say on this point. I'm sure
Q,
he has an opinion.
We could have you can have the last word.
Well, I think science is not about words. Science are about the results. So I showed all the results. So I have nothing more to say. Yeah, I mean, when I say some words that will carry my emotion and some thought, but
no,
you know,
very
the results, the results are the method I could use, the most affordable and the best method I could use at the same time, and the results are as they say. So I think the results speak themselves. You know, as I said, I'm in a sense, my thinking and my feeling don't go with the result fully. If you understand what I try to say. So actually, it's not so meaningful for me to say something because the results have already spoken, and what I say don't mean very much. And I will keep doing the additional analysis from additional angles. As I said, I did in a sense two extremes. You know, one extreme and the other extreme, and they agreed. So I would like to see more results. But I already mentioned the areas one can do more. So hopefully younger generation people will do more work. And then I think we should remove all the emotions and the thinking, just to try to get the results, what the data say. Yeah, that's the only thing I had in my mind when I, had a disagreement with Indranil, and then I even told him, let's not, tell each other which results we are getting, because so that we are not biased by others' result. And then actually I put my results on archive in May, even without telling him. So they may have been surprised by the result. So I'm still the same. So, but as I said, my thinking and my feeling, my understanding don't fully go with these results. But these results are correct results based on correct methods.
Yeah, so as Xavier agreed, so if we say this, that your result disproves Newtonian gravitation at low accelerations in wide binaries, to that you would say yes.
Yes.
Yeah, I agree. Yes, I think that's a good takeaway point. Of course, a very important takeaway point. Yes.
Yes. So the MOND paradigm is the basic tenet of a MOND paradigm is that the gravity breaks down without dark matter. So that tenet, that claim has been proven, not specific MOND models. So we don't even have a good MOND theory. So A-core is just a phenomenological model, so that describe data well. But that's we have proven the basic tenet of MOND. That tenet says Newtonian dynamics breaks down at low acceleration without dark matter. So in this wide binary, dark matter plays no role, but Newtonian dynamics breaks down. So now Newtonian dynamics breaks down in two extremes. In the relativistic limit, it breaks down. Now in this low acceleration limit, it also breaks down. So I think it's not too surprising. Newtonian
relativistic
has broken down many times. Quantum mechanics, relativity. Yeah, so why not one more? Yeah.
Yeah, I agree. Yes, great. So I think we should start winding up. It's really great to having both of you and other participants. It was a wonderful talk. Sorry, Q, for keeping you awake till so late, but we are really thankful that you could come. Michael, you want to say something?
I don't really think I have anything significant to add, except to thank, obviously, both Xavier and Q for a marvelously detailed and clear exposition. It was a fascinating learning experience. I'm afraid my own background in astrophysics is such that I could not really add anything of relevance, except perhaps one thing, which was that at several points in the discussion, I very much was reminded of an extremely interesting talk which I heard about a week or two ago in an online seminar that I follow from a German university, which is actually about applications of AI. And it was about applications of AI to data assimilation algorithms in climate science. And I will send the link, because I think some of the methodological issues relevant to to data assimilation and to when detecting the suggestion that there might be something suspect in something like curve fitting going on, and when to exclude that, which were an issue in that work. It seems to me, as speaking as a complete outsider, I'm afraid, to astrophysics, possibly also have some interesting applications here in the debate on MOND. But it was absolutely fascinating, and thank you again very much indeed for the very, very clear exposition. It would be wonderful, of course, as Xavier said at one point, if in the next generation, or the next generation but one, of observational evidence from the next generation of satellites, one could find something where we could go beyond reliance on the statistical evidence and actually find an absolutely clear, the equivalent, as you said, of the perihelion of Mercury, in the case of one absolutely clean example of wide binaries, which would perhaps decide the issue. But as I say, that may be on the horizon in the middle term future. Anyway, once again, I'll stop burping and thank you both again for a really marvelous session. Thank you.
Once our timetable is clearer, we'll definitely send you out an invitation for a talk early next year. We really look forward to your lecture.
I'll be delighted.
Great, thank you.
Yes,
thank you.
Please. We would be delighted. I think we can both say, I'm just speaking for myself, we'd very, very much like to come back and revisit this issue again, and we certainly plan, as you probably know, to have more MOND related talks in the next year of this seminar.
Well, I mean, I'll just add something from the point of view of MOND, or of the sort of astronomer's point of view of MOND. Nobody believes MOND is a theory, okay? We're all aware that we're dealing with a sort of back of the envelope scaling laws, sure, which are pointing us in an interesting direction. Let's say away from, certainly from Newton, and hence, since we are in the low velocity regime, away from GR. but we don't really know where on earth we're being pointed at, no?
No, no,
Yeah,
no.
maybe, Xavier, that's a very tempting point for me. We'll have a paper
Yeah.
coming out in the next few weeks on something called dark electromagnetism. It's a U1 gauge theory, which is relativistic, and we are trying to make a case that that's the origin of MOND. I mean, it's like a SU2 cross U1 GR cross MOND kind of theory. It's the analog of electroweak. So that's why I'm so interested in listening to
Can I come in super quickly on that to Jinder and say what the posting which Hillary just put in the chat, which is that essentially MOND is a body of very suggestive and interconnected phenomenology rather than a theoretical framework. I mean, I think that is certainly the take-home message I get. And sorry. What I was going, sorry.
You finish.
Sorry, yes, I do apologize. I will finish. I think that one of the most interesting topics for our seminar going forward over the next year and even beyond, going forward, would be both to hear more about this very, very rich phenomenology and observational evidence around the whole MOND program, but also, as you've just indicated from your own remarks, to hear more about some of the proposals for putting theoretical underpinnings under MOND, and you've just mentioned, of course, your own interest in a program for that. And I would just like to advertise those of us who were in St Andrews at the MOND conference back in June may remember the talk by my good friend Igor Konachikov, who of course has a proposal based on his own pre-canonical quantization program, his own proposals for so-called pre-canonical quantum gravity, which he seems to think provides a rather natural underpinning for some of the MOND phenomenology, and that's another talk which perhaps we might hear in the course of the next year.
Yes. Well, one more thing to mention, that for me it was very striking that the MOND acceleration is proportional to square root of mass and not mass. And I see that the way that is handled in AQUAL is you modify the left-hand side of the Poisson equation.
Yes.
The right-hand side source is still mass density.
Yes, yes.
What we come up with is we don't want to trouble the left-hand side. The left-hand side is still Laplacian of phi, where phi is a new fifth force, but the right-hand side is a new source which is proportional to square root of mass.
Yeah,
so,
as I understand it, that point that it is precisely mass density is very relevant also in Konachikov's approach in his suggestion. The framework that he's working on, that is also that fact becomes very salient also in their approach.
Somehow I've seen that in MOND studies, the square root of mass is not emphasized so much, but it's at the heart of the thing, along with the 1 over R. It will give, it's what will give you Tully Fisher.
Absolutely. I absolutely want to say amen to that.
Yes. Yes, great. So maybe we could wind up, Michael.
Yes, by all means. And once again, very big thank you to everybody who participated, but obviously, especially to our two principal speakers.
Yeah, great. So I'll log out now. Good night to all of you. So
we'll see you next week.
Yeah, so Xavier, I hope you will come next week so we can tell Banik about our views.
The candles.
Yeah, and for Q, it might be too late, so I don't insist because it will be, I don't know.
Oh, yes, it's going to be the middle of the night for you, LSQ. But still, of course, you will be able to see the recordings. So,
okay, bye.
Bye-bye.
Once again, thank you all very much indeed.